Hey everyone! Today we're going to talk about Routh stability analysis and move into some direct substitutions. So a Routh stability analysis builds on our last lecture where we had this characteristic equation 1 plus g open loop of s equals 0. So we really want to be solving for the roots or the s values, and we want to see if the polynomial has any roots in the right-hand plane. So what we're trying to really find with that is an evaluation of all the potential coefficients that go from an to a0 in this system. Now, technically, in order to build out our system further, there might even be further where they're like a down -1, a down -2, and so on. But we're trying to solve for anything where these are potentially true, that a of n is greater than 0, meaning whatever that coefficient really is, it is greater than 0. And that means it's not equal to 0, it's not less than 0. Every coefficient has to exist and needs to be greater than 0. If, for point 1, any of those coefficients, those a terms, are going to be 0 or will be negative, then the system will be unstable. That means that at least one of the roots is in fact in the right-hand plane when we talked about stability before, and thus it is not going to be a stable system. So how would we solve this? Well, if it's not inherently clear and that we don't already have a unique polynomial for that, we would need to create one and identify the coefficient values. So we would use what's called a Routh array, which I've written up here, where we have the number of rows that correspond to n plus 1, where that n term is from here. We have an n order system with n plus 1 polynomial coefficients, and that's because we have, you can see, of 1 through n for all the coefficients here, but there's still a last one, a0. So that means we have all those n coefficients plus one of them. So we'll create a number of rows and we'll just number them 1 through anything that leads to n plus 1. Then we need to actually write in, for the very first 2 rows, our coefficients. And so we're going to start at the very top left. We're going to move down, then we'll move up, down, and keep going across until however many that we may have. Then, afterwards, we will break down into our B coefficients, then C's, then D's, E's, F, G's, all the way down to Z's. And we'll just break them down into being exactly how many columns that there are. So in those columns, we need to make sure that for those n plus 1 rows, the first 2 rows are actually going to be coefficients, and then we break them down into Routh-based coefficients. Now those help to resolve back for our system and help to make sure that we're actually in a stable environment. So in order to solve this out, we would actually need to then build a matrix and use determinants to solve for these. And so we can actually solve for each of these specific terms based on those determinants. So to solve for each one, we would need to build a determination matrix. And so I've already written out the solutions to a couple of these, like B1, B2, and so forth. But really all we're doing here is, let's take, for example, B2. If we wanted B2, we're just going to look up into the 2 rows above it. And we're going to say, okay, well, B2 is going to then need to be some type of multiplication of the 2 things above it, and also to the left and right. So you can think of it as, we're going to break it down as anything in its own, what's left over. So by eliminating these terms, we're left with only the things above, so we're really left with these 4 potential terms to work with. And of those 4 terms to work with, it's a negative determination matrix over one of the leading coefficients. So the leading coefficient we'll choose is the very first one that we would work with, an minus 1, and that will be our approach to moving forward and solving this base term. So in this case, we would have an minus 1 multiplied by an minus 4 minus an minus 1 multiplied by an minus 5. And we could do that for each of these. In the B2 term, that would then be what we just solved. And in the B1 term, that would be, we would have this term eliminated and we would move forward into the others. And really this starts to move into a standard approach forward. So we can take these terms forward and approach them for solving as we continue to go. But notice, for the C term, we would actually move up by 2. So we would only be considering the 2 above it still, and we would be solving for those base terms that are present. And so a way to solve this would be to always look 2 above and then create a determination matrix of those inherent values. So as time goes on and using this, we're going to run through a couple of examples to how you would actually solve this. So we're going to erase the board and start with our first example. We're going to have our first example here, which will be s to the 4 plus 5s cubed plus 3s squared plus 1 equals 0. So we need to write this into our standard polynomial form and identify those coefficients. So in this case, our n highest is going to be 4. So we can write a to the 4, s4, a3, s3, a2, s2, a1, s, a0 equals 0. So this would be our standard form based on our highest order of our roots, which is 4. So let's find where those terms match. So here in matching the very first one, we see that a4 must be equal to 1. Next, we have a3. That looks like a to the n, must be equal to 5. a2 is equal to 3. a1 must be 0. We don't have anything there. And a0 is 1. So luckily, all of these coefficients are positive except for 1. This one is 0. So it is neither positive nor negative, but the rule states that all of them have to be positive and non-zero. So because one of these is 0, it is unstable, unfortunately. So a little frowny face. This is an unstable system. We know that immediately. There's no solutions needed to identify what the coefficients are. But let's say we move into something a little bit more complicated. So let's say that we have example 2 is 10s cubed plus 17s squared plus 8s plus 1 plus kc. So when we identify this system and we look at it, we can see, okay, well, our highest is 3. So we know that a to the 3 is 10. a2 is 17. a3 we already solved for, so we're looking for a1, which is 8. And a0 is what's left over, so 1 plus kc. So we need to identify conditions for which that's going to allow for this to be true. Well, we know that because a0 has to be greater than 0, that means that 1 plus kc has to be greater than 0, or kc has to be greater than negative 1. So this helped us solve our lower bound of the system. So I'll write that down for stability. Let's use our Routh array to see if there might be any other stability terms that may help. So we had n equals 3. That means our rows is going to be n plus 1 or 4. Our coefficients we can add in next. That's going to be our a3, a2, a1, a0, and we'll just move it on forward to an a minus 1 and a minus 2. So in that way, we can say, all right, well then we have b1, b2, b3, c1, c2, and c3. We already know what a lot of those terms are, so we know that specifically a3 was 10, then we had 17 for a2, 8 for a1, 1 plus kc, and in reality we don't have an a minus 1 or a minus 2, but I'm just going to write them out anyways. This will end up being true. So in those cases, if you need to, you just write out zeros, and that's helpful. So we need to solve specifically for b1, b2, b3, c1, c2, c3. So we can do that. If I try and solve for b1, that will be 17 times 8 minus 10 times 1 plus kc, all over 17. And that's because I did the negative determination over our a2 term. So in that case, that will end up being about 126 minus 10 kc, all over 17. We can then try and solve for b2, where that would then be based on the multiplication of other factoring terms. So in this case, that will end up looking like 17 times 0 minus 10 times 0 over 17. So that's 0 minus 0 over 17 is 0. So this is actually going to be 0. My B3 is going to be based on 0 times 10 and 0 times 17 as well. So that will end up making that 0. So if we try and solve now for C1, that will end up being based on the two higher. We have 17 times B2, but B2 is 0. So we have 17 times 0. I'm going to do these as a negative for each other. So negative of that minus B1 times 1 plus KC over my initial term coefficient down here, so B1. That is going to be negative of a negative. C1 is going to be B1 times 1 plus KC over B1. The B1s factor out, and C1 is equal to 1 plus KC. So what's really interesting about that is, in reality, that is the same thing as what we just saw for here. That really just gave back our initial term of A0 anyways, which once again states our lower bound of the system. Let's try and solve for C2 though. C2 is going to be based on the multiplication of these matrices. So C2 is going to be 17 times B3, which was 0, minus B1 times 0 over B1. So that's also going to be 0. And based on the math of you kind of probably can already figure out, this is also going to be 0. And so we get this really unique system in which we end up having this like trapezoidal effect, and that's pretty standard. But this really comes from the fact that these terms were already 0 anyways, and that we didn't really need to consider them. But based on having us move down here, I wanted to try and create like a 4x4 matrix in order to see what that might look like. It's very helpful just to do it anyways, and then if they end up being 0, then they're 0, and no harm, no foul. But what we've done is we've essentially solved through the full Routh array, and we've seen what each term may equal. And while this term was our lower bound in particular, and all the other terms are solved for, we actually do see another boundary that we haven't been looking at, B1. So if all of these terms, B1, C1, and so on, all have to be greater than 0, then that means that in this case, if B1 is greater than 0, then 126 minus 10 KC over 17 is also greater than 0. So if I were to go ahead and just negate the 17, multiply by both sides, 126 is greater than 10 KC. If I divide both sides by 10, KC is less than 12.6. This will be our upper bound. And so what we've done for stability is we've actually identified two conditions where KC has to be both, on a sense, less than 12.6, but greater than -1. And this will allow our closed loop system to maintain stability. But we wouldn't have seen that before. Just inherently looking at this system here, we wouldn't have just thought, oh, of course, this is the case. But the Routh stability array helped us to identify both a lower and an upper bound based on the terms that remained in our system. And this is really interesting. So hopefully this sheds a little bit of light indirectly how you can use this, but we're going to try another approach next that's going to really take this to the next level. Let's move forward with direct substitution. And we're going to use that same example again. So a direct substitution method brings us back to the right and left-hand planes that we've been talking about for a while. So we have these imaginary lines of S and our real of S. So this is our plane of S space, and we're looking at, with specifically our poles, where there is stability or instability. So here is the area of instability. I've just written unstable with the frowny face. So the direct substitution method helps us to identify exactly where this happens. It is the exact point at which stability goes to instability, meaning it is on the imaginary line. So what if we potentially were to try and identify a system in which this could be true? So let's find a line point S equals JW, where J is I could use J, but they're both going to be an imaginary number. And they're going to allow us to identify this destabilization point along that line where we can substitute that into our characteristic equation directly. And so we can solve for, in this way, our Kc to be equal to Ku for where the characteristic equation ends up being an ultimate gain. So if we were to plug this in, then solving for Kc will have us actually be solving for the ultimate gain of our controller in that system. So if the gain is increased past this, the roots will end up crossing the imaginary axis, because this is based on that, and will lead us into an unstable base system. So for systems that are second or higher order, the proportional controller will have this ultimate gain value, and it will really allow us to then produce a purely oscillatory response with some frequency of W. So we're just solving for that to be true at any point. But notice that this would be based on also a real term. But we're on the real axis being 0 exactly here, and we are just simply saying on any point of our imaginary axis. So we're just looking at the imaginary. And that's it. So how can we use this? Can we plug it in directly? And what can we use for solving for that specific corresponding frequency at those points? Well, let's go back to our previous example. So I'm going to pull that example up, where that example was specifically 10s cubed plus 17s squared plus 8s plus 1 plus kc is 0. And so now, if we try and substitute for those terms in particular, then we are going to use where s is equal to jw, but there's a couple of things to remember. These are imaginary numbers, and so imaginary numbers have interesting powers. For example, what happens if s cubed exists? Well, s cubed is going to be considered as s cubed times, in this case, 1, where that's also 1 cubed in that case. But what's really going on here that's interesting is if we plug in, then that's jw cubed, which is j cubed, w cubed. There's a lot of ways that you can think of that. But j cubed is then going to be equal to, well, j times j squared times w cubed. And as we know, j is equal to I, which is equal to the square root of -1. So then j squared is equal to -1. So in that case, that will end up being a negative term for itself, but we still have a j that's present. And what we're trying to do in this direct substitution method is we're going to solve for the real component and the imaginary component. So that j is fine, because that means that we actually can solve for that piece as just imaginary. But that j squared is -1. So let's use this directly. Let's substitute s is equal to jw. Oh, I am just outside the plane. S equals to jw, and that is 10. Our s cubed is going to be j times -1 w cubed plus 17s squared. Well, that's going to be negative w squared, because we are going to have a j squared. Therefore, that's -1. Then, afterwards, we're going to be able to solve directly in for our 8s, where s is going to be jw, plus 1 plus kc equals 0. So let's try and identify the term that's real, and let's try and identify the term that's imaginary. So let's go start with our real term. So we have a real term here of -17w squared, then we have imaginary, then we have more reals, 1 kc, plus j, we're going to pull out of the expression for imaginary term, and the imaginary coefficient to that is going to be -10w cubed plus 8w, and all of that is going to be equal to 0. But for this to be true, we know that specifically both of those pieces are then going to end up being their own equations that will also equal 0. So for our real term, that's going to be its own first expression, where that real is going to be -17w squared plus 1 plus kc equals 0, and our imaginary is also going to equal 0, which is -10w cubed plus 8w equals 0. And both of those are true. Both of these are going to be the frequencies that correspond to our ultimate gain and where we actually will have our ultimate gain. So if we plug in Kc is now Ku for our ultimate and W is our ultimate frequency, then we can actually start to solve for these directly. And so we would see, okay, well, we would have W cubed and W here. We can use that to solve directly for what our W term would be. So let's make this 10W squared equals 8. That's because I just added the 10W cubed to the other side and divided by 1W term. W squared is equal to 8 over 10. WU is equal to plus or minus the square root of 0.8, or 8/10. Great. Well, we can plug that into here directly, where for the real term, we would have Kc equals 17W squared minus 1, because I just added and subtracted those to the other side. That 17 times W squared was 0.8, or 8/10, minus 1. So if that's going to be times 8 over 10 and 10 over 10, then 17 times 8 minus 10 was 126 over 10, or 12.6. Interesting. So Ku now is 12.6 with a frequency of plus or minus 0.8. And that is really interesting because that is in fact the ultimate gain. If you remember from our previous example, we did in fact have the condition that Kc had to be between -1 and 12.6, and we've now reached where that would end up being its maximal possible value, giving us the ultimate gain of our system. And we did that just by direct substitution. We plugged that in, we identified a unique frequency, and the equations together solve for our two unknowns, which were the both of these. So we can end up using this type of expression to solve for these terms directly, and we can end up plugging that right back into the initial equation where we can use this to solve for that. Now, I do want to note that frequency is in units of rads per time for S, meaning that if S was in units of 1 per minute, then we're looking at essentially how the unit time would be based on minutes. And it would be like time units based on minutes, radians based on else. So we can use this to help to solve for rads per time unit in general, and how that expression would end up being valuable. So how does this relate back to the Routh array? How would we use this in conjunction? Well, specifically, we had just solved for our Routh array previously. I'm going to write it back up. We had said that we have this 10, and then we had the 17, 8, 1 plus Kc, 0, 0, B1, B2, C1, C2, and where these are both 0, and that's also going to end up being 0, where we essentially have that trapezoidal effect as I showed before. But something interesting to note, something really interesting. We saw before our lower limit ended up being C1, and our upper limit ended up being B1. But notice the upper limit was, in fact, Ku. So in that sense, what we're really seeing is that Ku is the gain directly yielded based on the nth row or one row above the bottom element when that's equal to 0. Or at the nth row unit. And that was true because B1 ended up becoming that same case. And if we want to solve for that again, B1 in this case was 17 times 8 minus 10 times 1 plus Kc over 17. That ended up being, in that sense, 17 times 8 minus the 10 was 126 minus 10 Kc over 17. And we just said that this must then be the condition that Ku ends up being the gain at which B1, or this nth term first condition, is equal to 0. That 17 cancels out, and 126 equals 10 Kc. Kc, which is now Ku, is 12.6. And that ends up being true. Furthermore, we can actually solve directly for our frequency term based on the relationship of K2 to K1, where, in this sense, we're looking at K1 being the element in the first column of the n-1th row, where K1 in this sense is directly going to be this 1 plus Kc term, and K2 is going to directly then end up becoming this 17 term. So what we're looking at is the element in the first column of the n-1th row, 2 rows above at the bottom, and the element in the second column of that row as well. So if we take 2 from the bottom all the way up, we get these specific terms that end up being our K2 and our K1. And so we can use that directly to solve for them. Oh, I actually think I put these backwards. My apologies. Yeah, because it's the first and the second coefficient here. So that should be a 1 and that should be a 2. And so that should end up becoming square root of K2 over K1, which is our K2 is the second, then over the first, 2 rows from the very bottom. So the n-1, that's n plus 1. We would have K2 over K1, the square root of that. We just found what Kc or Ku is here, where that's going to be 1 plus 12.6 divided by 17, square root of that. In this case, we're going to get square root of 0.8. And so that is something we can directly solve for. And so the Routh array, if we use these types of expressional terms, where we're looking for this to be true, where this is going to be where we're setting the first coefficient term of the n itself, so the nth row, we can solve this. And we can use either based form. But we're trying to solve for an ultimate game based on direct substitutions in our system. And so hopefully this identifies some criteria limits for lower and higher stabilities for our system. This again is for a proportional controller. Soon we're going to move into more complex systems, but for right now, these are interesting approaches to help to solve for the system. So thank you for your time, and I look forward to the next lecture.